Welcome, everyone. Thank you for your patience while we resolve some technical issues. I'd like to welcome everyone to the session Humankind in Outer Space. I'm Dr. Jim Myers. I'm a professor in the Space Studies and Earth Sciences program here at American Public University Systems, one of the sponsors of the conference. If you have any questions for our presenters, you can type them into the chat box, and we will have a question and answer session at the end of their talk. It's now my pleasure to introduce our presenters, Dr. Gonzalo Munavar and Philip McMurray. I'm going to make myself disappear here, but I will be in the session while you speak, and I'll come back on for the Q&A.
I'm trying to get my picture up there.
Well, I wouldn't worry about it. We'll just start the talk. I wouldn't worry about it. They can hear your audio just fine.
Why isn't my picture up there, though?
I don't know, but just go ahead.
Okay. This is Gonzalo Munavar, and I'm giving this talk with Philip McMurray. We have the first half, Humankind in Outer Space, is based mostly on my book. The Demon of Starlight, the philosophy of space exploration. You can see the picture there, a picture of the Earth from the moon, and published by Oxford University Press. Basically, well, mostly chapter 9, but other chapters will also play some role. Okay, so now, next slide. Okay, now I think I have to apologize. We may have some problems here. I have been quite sick. I just got out of the hospital yesterday, and we will, but we'll try to do it now. I'm having some problems right here with this. Now,
so with
was that the next slide? I saw the next slide.
Yeah. So
with the philosophy of science.
No, the space science and serendipity.
Okay,
so,
all right. Let me go to this then. The nature of scientific exploration creates the conditions for serendipity. That is, for finding new things that may be quite agreeable to us. Okay, serendipity makes all scientific exploration, space exploration, practical in profound ways. And this is based on the nature of science. Next slide. Yeah. The nature of science, and people talk a lot about the scientific method, but they talk about it wrongly. Generally, it is thought that the scientific method is based on how observation passes judgment on theory. For example, the accuracy of prediction. And this is also called empiricism. And this idea that observation justifies what we get in science, is prevalent. And actually, the person who came up with this was Aristotle. But it is not Aristotle, it's Galileo who is considered the big hero of the scientific method or empiricism. But Galileo instead draws a dagger through the heart of empiricism. And that is because of one very important point that he made. And this is where philosophy and all that is involved. Okay, observations make theoretical assumptions. So observations are not the base for justification. They actually themselves make theoretical assumptions. Next slide, please. And consider this picture. It's an argument that Aristotle gave a long time ago, 2,000 years ago, 300 years ago, I think. You have a tower, you go up to the tower, and you drop a stone. And what happens? This stone falls vertically and hits the base of the tower pretty much at the same distance that you let it go with your hand way up there. That's what we see, what we expect. That's what millions of people see. That's what actually billions of people see. Anyone with eyesight, with good eyesight, or even decent eyesight only sees this. So it's observation at its very best. Now, what is the consequence of this observation, though, in this tower? Well, the consequence is that Copernicus, the guy who told us that the Earth, or who proved, we think he proved, that the Earth actually goes around the sun, not otherwise, and that the Earth is thus not the center of the universe. That guy, Copernicus, who started the Copernican revolution, which led to what we normally now call science, is well, what? Completely wrong based on observations. Why? The stone we see fall vertically, that's the observation. But if the Earth moves, which is what Copernicus needs, because the Earth not only moves around the sun, but also it rotates. If the Earth rotates, then the Earth is going to move. And by the time the stone hits the bottom, the soil, then the stone will have moved. And so if it hits vertically, it will be far from the base of the tower. And actually, at the distances that at the speeds that the Earth was supposed to be moved, according to them, in those days, it would have been quite a distance. So it's clear that if the Earth moved, then the observations that we would see of the falling of the stone, this make a mess of this. It could not move. Okay. All right. Next slide. So what Galileo then thought was, well, look, we actually have a different picture. We have an actual motion that is the Earth moving around is an actual motion that we share, the observers share, the tower shares. Okay, the stone doesn't when it's falling down, except in the fact that it also has a motion. So the stone actually has two combined motions. There is a natural motion and then the observed motion that we see of the stone. So we have a natural motion, which is as we have said, from the Earth, and then we have an observed motion of the stone, and the actual motion, which is somewhere in between, a combination of the two, that today we will do with the mathematics that we now have. Okay, so next slide, please. So that is what happens, that you come up to a point where your view clashes with observations, and then you nevertheless determine that there must be some assumption. And the assumption is, in this case, that the Earth does not move. You have to assume that the Earth does not move in order to conclude that the real motion of the stone is straight down. And of course, that is mistaken. And then the Earth does move. Okay. Now, one back, please. Okay, it says space science and serendipity. Then, as we have seen, there are instruments for interacting with the universe, and they tell us what the universe is like. And scientific views determine what problems, dangers, and opportunities we can be aware of, because we discover what assumptions we are making, and we change those assumptions. With changes of worldview come the realization of new problems, dangers, and opportunities. And by becoming aware of new problems, dangers, and opportunities, we also become able to think of new solutions and new technologies. That's why space exploration has so much to offer us in all fields. Go ahead, next one. Many problems we face today cannot be solved unless a different point of view comes into plan. This is the philosopher Feyerabend's point of proliferation. Okay, space exploration offers a bounty from space because exploration presents many challenges to our science and our technology. Since space exploration contributes to transforming our views, investing in it has a clear advantage. Next. Okay, this is the serendipity then model of scientific change. Scientific exploration leads to scientific change, which leads to serendipity. Okay, next. Okay, now space exploration in the long run. Space exploration will eventually go beyond the moon and Mars, and by this I mean manned or human space exploration will eventually go beyond the moon and Mars. There are two serious problems with this, and one of them is radiation exposure, and the other one is microgravity. In a trip to Mars, it would take about 7 months or so, and that is an enormous amount of radiation and enormous amounts of microgravity. And people think that these problems can be managed, that they can be managed. Next one. Oh, please go back. That this
So,
can be managed by having some medical procedures that will handle both radiation and both microgravity, but these procedures do not work very well. Some of the procedures that to die with radiation exposure require extreme new make medical exams and surgeries and so on. And then if you have one, you have to have another one. And the result is a terrible, terrible medical condition that is too inhuman to inflict on people. But we can deal with them actually in a much, much simpler way without doing all these terrible things to human bodies. Next one. Okay. One of them is that we can have a way of living in space that, as in an O'Neill space colony, in which we have no problems with the gravity, because we have artificial gravity, which is provided by motion. The O'Neill colony rotates, and it's big and rotates, and that rotation gives it the equivalent of the gravity. It could be almost as high as G, our G1, okay? And also, it has a very thick protection of the spheres by against radiation. By the way, that includes some new plastics that and other substances that NASA has developed, including nanotubes, is hydrogenated boron nitrate nanotubes. If you have the water, or let's go to the next one. This is a spaceship. There are two important points about the spaceship. But anyway, in this spaceship, the outside of the human transport compartment, which you could see at the bottom of the three that are shown, water is on the walls and on bags, in plastic bags, and that water will do or stop much of the effects from
from the effects of radiation.
which is the radiation that does the most damage. And on top of that, NASA has developed this nitrate nanotubes, which is hydrogenated DNAs. And this is an ideal shield against radiation, both for spaceships, but also for dwellings and vehicles on Mars. So you could see this in my book, on page 169, actually, as a matter of fact. Okay, and then one important thing is that we are used to having spaceships shown as having first the the engine, which is a rocket, and then after the engine, we have a second compartment, which is, I mean, on top of the engine, which is the supply shop, and then we finally have the human transport at the very front, and then this is how the rocket goes to space. But this is not the best way. Actually, we should transform this. So we have the three of them in this uh, form that you see in this picture drawn by Phil, by the way. So we have the combustion rocket, excuse me, and then you have on two sides of it, and we're talking about a couple hundred meters or total, the supply ship, and you connect that way to the supply ship, and you can also connect down to the human transport. This is just a tube that connects them strong enough so that the three of them will stay together. But then the ship will be propelled all the way by the rocket, and at the same time, it will be rotating, and this rotation will give to the human transport and to the supply ship the gravity. And so artificial gravity, and this is how we'll make it without all those terrible diseases from cosmic radiation and from microgravity. Next.
Yeah. Oh, and one other thing, it's a very slow rotation as well. The ship is moving, it's very slow. So it's not like it's going don't imagine it going very, very fast where it would disorientate passengers. It'd be a very slow, but calculated enough to keep it at 1G, so it's not really noticeable that well to the passengers on the ship. So yeah.
Okay. Now there is the question then of how fast we can go, because star systems are extremely far away. So we could send thousands of scientists, but how long are they going to take to get there? If they die, it's not guaranteed that the next generation that they can put up will be exactly like them with the kinds of training and so on that they have, and the talent that they have to be good to do science. Okay, so travel to other star systems, which are light years away, is not feasible, they say, without achieving it's not feasible without achieving velocities close to that or higher than c being the velocity of light. Many physicists, however, believe that Einstein's special theory of relativity makes it unfeasible to accelerate the starship close to c. Problems? Some believe that speeds higher than c will be impossible, and also problems with solving fuel storage and shortage problems. Okay, let's go ahead to the next one. Okay, this is the famous formula from which people draw such conclusions that you cannot really accelerate a spaceship close to the speed of light, and that you cannot go beyond the speed of light, and that, well, other things. So we have mass, this relativistic mass, is equal to rest mass divided by the square root of 1 minus v squared over c squared. V squared is the velocity of the ship with respect to the observers. The observers probably on Earth, just looking on to see what's going on. And so is the mass. This is relativistic mass with respect to those observers. So what they say is, look, when the velocity increases, V2 over C2, gets closer and closer to 1, right? Because V gets closer to 1. Please go.
No, you
Okay.
probably want to stay here.
Okay.
You're
Well,
really here now.
when it approaches 1, then the denominator approaches 0. making mass infinite. Let's go back. Let's go back one. Okay. So you can see there, v squared comes close to c squared, and this 1 minus v squared over c squared becomes very, very large. Excuse me, very, very low, close to 0. And then when you divide the rest mass by close to 0, is a huge, huge mass, which they say approaches infinity. But you see, and then how we want to move this huge mass? That's the idea. How we're going to accelerate even more? But you see, there is no problem because the rest that counts is the rest mass. It's the rest in the ship. For the astronauts in the ship, the rest, the amount of fuel that they have, you know, the mass of that has not increased. It's the same. In fact, if the fuel works by throwing it out, burning it up or something and throwing it out the back, they have less weight, less than they have to begin with, the less mass than they have to begin with. So this is a confusion here. This does not affect the travel of the ship. Okay. And so let's go back to the next one. Okay. So the rest mass increases only from the point of view of the earthbound observers, but not the astronauts. And go back one more time, sorry, to the formula. Okay, now some people say the mass becomes infinite if the velocity of the ship ever reaches the speed of light, because then it will be v squared over c squared will be 1 minus 1 will be 0, and they think somehow that the rest mass divided by 0 is infinite, but that is not the case. In mathematics, this is not permitted. This is not a valid solution. So you cannot have division by 0. It's unpermitted. Okay, let's go forward in mathematics. Okay, there are some proposals for faster than sea travel, and then we will see two things in the rest of this talk. One of them is a proposal for travel very close to the speed of light, which will allow us in practical terms to get to at least the closest star systems to ours. And then we'll also consider proposals for faster than sea travel. I'm just going to mention them. So next one, please. One of them has been the proposal made to go through a Wheeler wormhole. And the thing here is that Wheeler thought that the very, very, very small, and there is this kind of a foam of materials, and this foam, will permit perhaps some very, very small tunnels to be formed. And these very tunnels, next one, you see, will allow us to, which he calls a wormhole, would allow us to, if we could go through them, we could go to another part of the universe completely, because the universe is folded, he thought. And if it is folded, at one point, the distance between here and something that, if we just look straight up, would be, far, far, far too far. But now, I mean, we're talking practically the other side of the universe or something, or even a different universe or something. But we could contact it because it falls, and it falls, the distance is not that large. And then if we could make a wormhole, then we'll be able to go through it. Now, the wormhole will have to be expanded. The walls will have to be treated in such a way that they don't collapse on the spaceship. But if we can do all that, then the spaceship will come up there, and the travel to another part of the universe will have not taken very long. And of course, could be considered as having gone a lot faster than light to a very, very, very distant galaxy. And the problem with this is that if this really worked, you could actually go back to your own part of the world, to your own part of the universe, and say, land on your grandfather, who is a child then, and kill him. And if you do that, I mean, this is in principle possible. The probability is extremely low, but it's in principle possible. And if you kill him, then you could not have been born. And if you could not have been born, you could not have made the trip in the first place. So you have this very strange problems that you can go back. These puzzles are connected with space-time. Space-time, excuse me, with time travel. If you do time travel, then you destroy the very possibility of you going on the trip that made the trip, to have gone on the trip in the first place. So this and other problems that actually they have with finding the wormhole, expanding it, and several other problems, which I unfortunately don't have the time to discuss now, makes it extremely unlikely that we will ever be able to go back in time, okay? And that we will ever be able to travel through space in this way. Okay, next one. Okay, then there is wonderful Alcubierre's Miguel Alcubierre's warp drive that he came up with in the 1990s. And the idea is that if you could make space-time diminish in front of you and expand behind you, then you could go faster than light. That is, the system, the space-time area in which you are moves a lot faster than light. Okay, so the ship, if this happens, next one, please. See, it's expanding behind him, and space-time expanding behind him and contracting in front of him, and that will make the ship go much, much faster. Okay, now the problem with this is that he has to have a mechanism by which this space-time could do this. And unfortunately, the only one that he has to offer is a strange matter or some other things that simply do not exist, or at least we haven't found yet. And so the Alcubierre warp drive has that difficulty. Next. Okay, now, so what if we could then go with close to space, close to the speed of light, excuse me, but not reaching it, the ones that we discussed before. So what you would do is have a Widmeyer mechanism, a spaceship. And then what you do with this Widmeyer is that you don't have fuel, you don't have to collect fuel and put it in the ship and have that ship go using that fuel. What you do is you get the fuel from space itself. There is hydrogen ions, and you run these hydrogen ions to what is called a Widmeyer ramjet. It has a nuclear mechanism inside. And next one.
Next one. Well, hold on. I'll explain a little bit about the Whitmire real quick. So it has these nuclear ramjets on the back. And then one of the problems with any sort of trip like this that would take assuming even at close to light travel, you're still like Alpha Centauri is only it's still 4.6 light years away from us. So even if we were going, let's say 0.8 C, that's still a considerably long time, and you need the fuel. And they're like, so the question is, well, how do you fuel it? And well, fuel could take mass on the ship and so on and so forth. But a great
Okay.
innovation about this is that the ion scoops, you could take the hydrogen from space, so you don't have to fuel
Okay,
the ship itself.
what we have is a catalytic nuclear reaction
Yeah.
cycle. And when these catalytic nuclear reactors, take in these hydrogen ions and they go through the reaction and then we get something out at the back that propels the ship and it continuously provides this reaction. So what we do is collect these hydrogen ions that will have stopped even the ship, instead tunnel it into the catalytic nuclear reaction. The catalytic nuclear reaction then provides the energy that propelled out the back that will move this uh, faster and faster and faster, and then closer and closer and closer to the speed of light. And then when he gets to the next, oh, by the way, here, this picture that I have is a Widmar Starship space colony. So you have a space colony of the style of O'Neill's, and it has 3 or 4 Widmar spaceships around it, propelling it and taking it actually to another star system. Once it gets there, then the scientists in them, in the space colony, which would take only about 10, 12, 16 years to get there, will then try to terraform the planets there. And that was actually provided a place for humans to go live in, coming with another one of this, and it would take a matter of dozens of years of these things, not millions. So that is the proposal for with the Widmar Starship space colony, used in combination with O'Neill's ideas. Okay. So exploration conclusions then that the fast interstellar travel requires high relativistic speeds, terraforming planets. We have some scientists doing this, and O'Neill space colonies with several windmill ramjets may work. And I again apologize for my problems, but I just came out of the hospital. Okay, so now we go on to Phil's part of the presentation.
Okay. So we talked a lot about theoretical stuff, but we're going to switch gears and get a little more grounded on Earth, and then more like, because this could be many hundreds of years from now when these things take place, but maybe we'll now talk about things maybe in the immediate 30 to 50 years. So, and we're going to completely switch topics, but they are related with space exploration and international relations, because as any space exploration goal, whether it's going to the moon again, whether it's going to Mars, or much, much further on in human history, hopefully to other star systems like Alpha Centauri, or even beyond that, at every step of the way, it's going to require international cooperation, because we're on Earth. There are many different countries and peoples together that need to work together to achieve big goals like this. It's important to also emphasize that because space exploration benefits everybody, we all benefit from the achievements of space exploration, from the serendipity that comes from new technologies, so on and so forth. Everyone should participate, not just the spacefaring powers. The world is not just the US, China, Russia, and India. There are many people in the global south and beyond that would love to participate in space exploration, so their inputs also should be considered, and are being considered with these international efforts. So when international efforts are good, we get very nice things like the International Geophysical Year, we get the Olympics, we get grand events of like many nations working together. When nations work together in bad ways, we get multilateral invasions. We've done things like that, war and destruction. So in the international relations realm and how this relates to space exploration, there's three challenges I want to talk about. Mainly a general disregard for international law, which has been very prevalent in the last 5 years in particular. Space militarization, ASAT testing, and then US and China, because that will be the biggest rivalry, at least geopolitically, especially when it regards to space exploration. So before that, though, a little bit of brief history. Of course, we all know about the space race and the Cold War, the race to the moon, the Apollo missions, so on and so forth. There was, of course, great geopolitical tension during that time. Um, in regards to like space exploration, there were some periods of relative ease and tensions, like the International Geophysical Year, which was a very successful international effort between the U.S., Soviet Union, and others, um, led to Sputnik later being put up in the space race, and Apollo Soyuz, the first international space station, mainly with the U.S. and Russia. So those are areas where it provided relief. But then in the 80s, there's more attention again. Ronald Reagan, the so-called Star Wars, the Strategic Defense Initiative of space lasers that could knock out ICBMs and all of the the tension that caused. And then of course after 1991, the Soviet Union collapses, and then we're in the post-Cold War era. And of course, there's reduction in tensions across the board. It's the so-called unipolar moment, if you want to use like Verschheimian terms of like, the U.S. being the only superpower in the system left, and really kind of not having any significant great power competition. And that was in many different domains, including space exploration, where really it's kind of in this period, NASA mostly doing its own thing. I mean, of course, there's collaboration with the European Space Agency and JAXA and things and so forth, but nothing like what we saw in the Cold War. Um, but then things are shifting in the modern day, and especially in the last 2010s as China's risen. It's been well talked about, well documented. The success of the Chang'e program has been, well, from a scientific perspective, very fruitful, but also from a geopolitical perspective, concerning, with China's rise, and so on and so forth. And of course, there's new players coming in where India is definitely taking the lead now of space exploration, Japan putting rovers on the moon, so on and so forth. So we're in a different world than we were 10, 15 years ago, even. So the first main issue of that derails international cooperation in space exploration and anywhere and any other activity is, of course, general disregard for international law. It's no secret that great powers break international law. In the past 24 years of this new century, international law has been broken many times. I mean, take your pick on what, war or provocation that we want to talk about. Just North Korea, of course, Russian annexation of Crimea. Now the war has expanded to a full-on Ukrainian war, and Chinese aggression in the South China Sea, where bullying their neighbors, being very aggressive, so on and so forth. This and or other factors have led to a real strong deterioration between the great powers, mainly the U.S. and Russia and the U.S. and China. And it's also led to, conversely, on the other side, this kind of tacit alliance that's now building between China and Russia to counter U.S. and Western interests. So you'll see some examples of this. So this is the Chinese Coast Guard being very friendly to their Philippine neighbors. Just they needed a little wash. Um, this is kind of routine where you have Chinese ships ramming into ships, doing very dangerous navigation maneuvers, or just spraying other ships in the South and East China Seas. Um, in fact, China has problems with all of its neighbors in this regard: Philippines, Brunei, Malaysia, Vietnam. It's not just the freedom of navigation problems. I mean, they're also being quite militant, building bases around the Spratly Islands for the past decade, and other islands, having territorial claims on islands that multiple nations have. So it's a real issue that could be very explosive. And then going beyond that, more recent developments, you see things from even non-state actors like the Houthis. Here's a picture of them onboarding a vessel to capture it. So you're seeing this, it's not just the great powers that are doing this. You're seeing, especially with the Israel Hamas spillover, lots of different problems.
Mm.
And then, of course, a war in Ukraine that's been full blown for the past 2.5 years. In short, there's a lot of problems on the international stage, and they're going to spill over into all areas of international cooperation, including space cooperation. So these things aren't in a vacuum. They're not in a vacuum. When great powers are having trouble economically or diplomatically, it will reach in many different areas and include space cooperation. It's been dampened in the recent decade. 2011, the U.S. Congress passed the Wolf Amendment, which bars NASA from engaging in bilateral cooperation with China. So in one of the very recent developments, Chang'e 6 went to the far side of the moon and it returned lunar samples from the far side of the moon the first time that we've received lunar samples from the far side of the moon. And the Chinese Space Agency they want to do basically what Apollo did. They want to have that same precedent of like sharing samples with the world. But it's unclear right now if NASA is going to be able to work with those samples without significant red tape because of the Wolf Amendment, which is still in place. So it leads to these tensions and problems. I mean, they're working on it, and hopefully that they'll find a way to get NASA these samples. But it just even the delay causes issues. Russia wants to leave. It has plans to leave the International Space Station, launch its own rival space station, despite the fact the ISS could stay functional, according to NASA, till at least 2030, if not beyond. So in this theme of spillover, when great powers disregard international law in one way, do they? Well, where does it end? If they have no problem with invading their neighbors and breaking X agreement here, X agreement there, well, in regards to space exploration, which we're here to talk about today, well, what about the Outer Space Treaty? What if great powers decide, well, we don't want to adhere to that anymore? Or if we want to militarize space. In fact, we want to put territorial claims on the moon, so on and so forth. This is something that any space enthusiast should be keenly aware of, and we're actively working towards preventing something like that. Not even if the prospect is unlikely, the prospect is never it's never a 0% chance, especially when you're dealing with great powers that routinely break agreements all the time. Focus mainly on U.S.-China because that will probably be the most significant great power rivalry of the 21st century. It'll be like how the U.S. and Soviet Union was in the 20th century. In some ways, it could be much worse. We just don't know. Of course, we have to, as things continue to play out. On many aspects, if there continues to be chip wars, the race to develop a more advanced AI, Chinese nuclear and conventional military modernization. So what's going to happen, in let's say 5 years from now, if China has nuclear parity to the United States, or their conventional forces are now they have beefed up enough to where they could threaten the United States in key areas. So South Asia, if we're talking about anywhere on the map that probably, if you had to put a probability on, would be the area where there would be the most problem long term, it's definitely South Asia. I mean, take your pick of what conflict that could potentially erupt at any moment. I mean, Taiwan alone, the South China Sea alone. China has problems with all of its neighbors, including India and Pakistan, which are both nuclear powers. India and Pakistan also have their own problems with each other. And of course, North Korea might decide to once again shoot a missile into the Sea of Japan. So there's many, many different areas that if they're not tapered down, we don't want it to derail space exploration. So the militarization of space. The big goal in the next decade or so is to establish a moon base. The U.S. and China have both said they want to do a moon base. China is going to do it with Russian help. So when this happens, and right now it's still in the very early stages, of course, but 5-10 years in a geopolitical sense is not a lot of time at all. So when the moon base, when continued Artemis and Chang'e missions um, make progress towards that, what will happen? Three concerns, of course, lunar territory. South Pole resources, where it kind of looks like the South Pole of the moon is a very attractive option to put a base for, resource extraction, for, solar power, nuclear power, so on and so forth. Um, Resource extraction. So what happens if, they decide to put territorial claim, which is supposed to be prohibited now under current framework? But again, um, it doesn't necessarily mean it would stay. And what happens if it doesn't? Resource extraction disputes, lunar mining, and well, even a more further thing, asteroid mining. So there's no current space law doesn't really address those issues well. But also they're not practical things yet because there is no asteroid mining or lunar mining to speak of yet. But in the next decade or two, that will be a emergent issue that will need to be addressed. And just militarizing space in general, which is not supposed to be done. But it is, there are being more steps to that. There are other talks today that talked about the possibility of, these satellite systems being used for use purposes. So, and how do you, in the security dilemma, how do you know if it's being used for a peaceful purpose or potentially adversarial purpose? And how do you actually define the lines between those two things? So continuing the conversation about moon bases. So of course, is the Artemis Accords, which here's a picture of all the nations that are signatories to the Artemis Accords, which is non-binding, but it's in theory and based on the principles of the Outer Space Treaty. And you do notice, if you notice, like the geographic distribution of the signatories, it's the West, some parts of it's mainly the West, and you have India, Saudi Arabia, and South America. Notably absent are China and Russia. They have their own agreement to for the International Lunar Research Station, the aforementioned the moon base that China and Russia are working together to hopefully they want to do together. So you're kind of seeing these two blocks emerge. The US and Europe on one end, and then China and Russia on the other end. You see these alternative things being made in other directions, like think of BRICS, like an economic union, um, various military alliances that are Russian or Chinese or Russian led. So now, I mean, even though China and Russia are also party to the Outer Space Treaty, the point is that you're seeing these blocks being made, these competitive blocks of a Western bloc on one hand and Eastern bloc on the other hand. That's not necessarily a bad thing. The competition can be good, but again, we want to make sure it's managed to the point it doesn't go out of control. And to talk more about the moon, I mean, the moon, of course, is a very attractive piece of extraterrestrial real estate. It has ice water, has many metals and minerals, iron, silicon, thorium, calcium. It has some rare earth minerals as well. Has helium-3 and this new, relatively new discovered material, Chang'e named after the Chang'e missions where they discovered it, which could be used for a variety of applications. So, and also great power, great source of solar power. You can put, many solar reflectors on areas of the moon because sunlight hits areas of the moon for much greater periods of time than on Earth. So it's a great potential source of energy, which means that there's great incentive for competition and war. That happens even more so if there's heightened tensions. So as we move into the next decade, into the 2030s and beyond, when some of these moves could be made a reality, we have to make sure that on Earth there's more diplomatic cooperation between the great powers and between all powers, so that when we do go to the moon, it can be an achievement much like Apollo 11, a step for all mankind, and not just for certain blocks of power, and not to the detriment of others. Because at the end of the day, it should again be something that should be considered an achievement for all of humanity and not just certain blocks. So here's a NASA concept art of like maybe what a moon base would look like as a nice lunar rover and things. Maybe they'll look a little more elaborate. I think this is from 2006, so maybe they have updated their concept art in like the Artemis era of things. But it's a nice picture nonetheless. So, in conclusion, geopolitical rivalries will influence decision making for crewed and uncrewed exploration. It's always been there, from the space race to beyond. It will always be a factor in significant things, decisions like that. So the next generation of space explorers, they need to focus on the challenges of their historical moment. They need to be aware of this. They need to be aware of the geopolitical situation going on, because they're not in a vacuum again. It's all interrelated. There's many different moving parts that need to be addressed together. So space enthusiasts should make sure that on many fronts, we are working together to achieve these goals, because they could so easily be broken if not for that. And international cooperation, again, has produced many, many things of value. So to continue that into this century and even beyond, to get those Whitmire ramjets, we need to continue to be mindful of it, especially in times of great geopolitical tension like currently. And then finally, just on a more broader note, space law needs to be respected and maintained to ensure future human achievement in space exploration. If there are no rules, or if there are rules that aren't abided by, they're essentially equivalent. Good governance and understanding what the rules are, what the norms and standards and regulations are, will ensure that everyone's working, even if there's disagreement, everyone's working towards the same goal and the same thing. So that is all for that. These references here, and once again, concepts like this are in the book, The Dimming of Starlight, Philosophy of Space Exploration. It's a great book for more detailed analysis on what his half of the talk was, and a little bit on the international relations, but not too much in that book. But either way, thank you very much for your time, and we'll be happy to take any questions.
Thank you both for thought-provoking presentations. Does anyone have any questions? If so, they can type them in the chat. Okay, I'm not seeing any questions appear. I do want to take a moment to give a plug for an event that's happening later as part of the conference. I'm calling it a Star Party at 9 p.m. Eastern tonight. There'll be a session that's focused on the American Public University System's fully automated or a fully remote astronomical observatory. Or I believe that if the weather cooperates, they're going to be using that, and there'll be faculty and students on hand also talking about some of the things that they do. So if you have a chance to attend that, I think it'd be a pretty interesting presentation or event rather. So hopefully you'll have a chance to check that out. All right, so I'm not seeing any questions. I think we can wrap things up for today. Just thank you again to our presenters, and I hope everyone enjoys the rest of their day.
Thank you.
Thank you.